Um, Thanks very much for the invitation to speak here. Thanks to you all for still being here in the last session of the afternoon. So I want to tell you sort of about a connection between quantum information, concepts from quantum information called quantum entanglement that of course many of you are very familiar with, and sort of geometry and sort of possible ideas for how this may be related to the emergence of space-time. And so this ties in both of the Tuesday session that I unfortunately did not have the chance to attend, so I apologize if there's repetition going on. But it also sort of, I'm coming from this probably from a different perspective, really from a perspective of quantum information theory, which is the field I work in, and so, but I hope it still resonates with sort of what was being said and discussed on Tuesday. So let's start with quantum information. So what is quantum information? So to us, it's really, to me, it's really just another word for, a fancy name for the state of a quantum mechanical system. So what are these quantum mechanical systems? The simplest such system we call a qubit, and we can think of a qubit as something concrete. Say the spin of an electron, a polarization of a photon, say, our two favorite energy level of some atom. But you can also think of this as an abstract concept, just a two-level quantum mechanical system, the same way that classically we reason about the bit, and we don't really care about how a bit is implemented. Now, quantum mechanically, if we have more than one of these smallest quantum mechanical systems, if we have more than one qubit, then there's interesting new phenomena, in particular the phenomenon of quantum entanglement. And the simplest such entangled state is often known as the EPR pair. EPR is short for Einstein, Podolsky, and Rosen, or the EBIT, sort of from a more quantum information perspective. EBIT, the entangled pair of qubits. So this EBIT is 0, 0 plus 1, 1 over here. So it's a superposition. It's the superposition of unentangled state, and this result we call it's sort of the fundamental unit of entanglement. It's really the basic resource for quantum computation, quantum communication. Without entanglement, we wouldn't have these, possible speed-ups sort of allowed for by, say, by quantum mechanics for future quantum computers. But it also gives rise, it's also the fundamental resource behind things like quantum teleportation, things like superdense coding, in particular Bell violations, which we, I guess, briefly discussed in the sort of question and answer session of the previous talk. So this was supposed to be a picture of the Bell experiment at Delft in the Hansen group. I'm not sure if that's very visible. Now let's talk a bit more about quantum entanglement. So we had this very dramatic state, this EBIT state that has all these very non-classical properties. We call it also a maximally entangled state. But in general, a quantum state of two qubits, see over here, is neither maximally entangled nor a complete product state. And so there's an interesting question: how do you actually measure, how do you quantify the amount of entanglement present in a quantum state? And sort of in information theory, what we like to do is we like to think about operational tasks. So we like, for example, to think about distillation problems, conversion problems, and so on and so forth. And so one natural definition is the following. Let's define the amount of entanglement as the rate at which you can extract perfect entanglement, perfect EBITs over here, from this arbitrary state on the left. And because we want to think of things in an asymptotic scenario, we're going to ask this question in a case where we're given many copies of this arbitrary but fixed state. We want to convert, we want to obtain as many copies of this perfect EBIT state. And this optimal rate, this optimal asymptotic rate, we call the distillable entanglement of such a quantum state. Now it turns out that if the overall system is in a pure state, that is, if all the sort of if the entire system is sort of a closed system, and it has these say two particles, the A qubit and the B qubit, then it's very simple to compute this rate, and it's given by this formula called the entanglement entropy. So the entanglement entropy is the same as the von Neumann entropy of either of the two qubits, which are being described by some density operator. It's not really important if you don't like the formula, but sort of the conceptual point is there's a very simple, clean formula that we can calculate, and it has a very operational meaning. The meaning is the rate at which we can distill entanglement. So naturally, if we have an EPR pair, then this rate is 1. We get one EPR pair out when we put one in. But if you have a state that has no correlation at all, then there's no way of getting out any entanglement, and so this rate would be 0. So those are sort of the two extreme cases. And in general, the number is just somewhere in between. Now, of course, entropy is a central quantity in information theory in general. This kind of quantum mechanical entropy is very central in quantum information theory. It appears in many other contexts, other kind of rates, quantum communication capacities, and so on. Are often we know how to express them using this entropic quantity over here. Okay. Now, suppose now we have not just two qubits, but actually many qubits, say n qubits. So, for example, we may be describing a many-body quantum mechanical system, some big piece of quantum matter. Then unfortunately, by the superposition principle, we have to keep track of exponentially many amplitudes. So we have this general state over here, but now there's not only 2 indices for 2 qubits, but n of these indices. And in general, we have to store all these many coefficients of the wave function front, and these coefficients make up a tensor. It's a tensor with n indices, and so the amount of memory that we need to represent this tensor would be exponential in the system size. And that is, of course, a problem, and that is what makes quantum mechanics so hard to simulate on a classical computer. But the good thing is that in practice, actually, things are not as bad. It turns out that in practice, the entanglement is quite local, and correlations decay, often exponentially, certainly very often polynomially, in sort of the distance between 2 qubits. And so this begs the question if we can find a more intrinsic description that is more efficient in representing such quantum states that sort of arise naturally in quantum mechanical systems. And so here's a very sort of concrete way by which you could go about this. Let's just assume that really the entanglement is quite local. So why don't we start with an extremely local state? So the idea is let's just take these EPR pairs, these E-bits, sort of put them on a, so suppose we want to describe a one-dimensional system on a chain. So let's take all these sites that you want to describe, and let's sort of share EPR pairs between sort of, any 2 sides. So each side would sit here. There would be 2 endpoints of these EPR pairs, and that would be an extremely local state, right? The entanglement would be sort of ultra-local, would only be nearest neighbor. Now, that's not going to be our state, but what we could now consider is that we could sort of, at each of these sides, apply local transformations, and we could sort of use these local transformations to entangle the left-hand side with the right-hand side, but still in a very local fashion. So there would be a transformation that has 2 inputs and 1 output. The output will be our actual physical system that sort of sit at this latter side. And so the picture we'll get is a picture as follows. So these red dots correspond in this case to 3 tensors, 2 inputs, 1 output, and we apply them to these EPR pairs, and what we get is something known as a tensor network state. And that is a very efficient description. Why is it efficient? Well, because we only have to store these 3-leg tensors, n of them, so that does not need so much space. In particular, in a translation variant system, you could hope that we actually use the same tensor everywhere, so that would be extremely efficient. And so it turns out that you can sort of describe sort of long-range entangled states very efficiently in this matter. Well, okay, we can discuss about long-range, but one example would be the so-called cat state, which looks like an EPR pair, a maximum entangled state, but it's sort of a macroscopic superposition. And this one we can exactly obtain in this way. We take a bunch of bell pairs, one sitting next to each other, and then we apply these local transformation rules, and it's sort of an easy exercise to verify that you'll get this cat state, the Schrödinger cat state out. Okay. So what we just discussed was an example of a tensor network. So tensor networks are descriptions of many-body quantum states. They're defined by, if you wish, taking bell pairs in some geometric fashion and doing local transformations, or equivalently, you take a bunch of tensors sitting at various points in space and you contract them in a geometric pattern. So what we just discussed was this matrix, this family called matrix product states over here, which is closely related to the DMRG numerical scheme. Another example would be the 2-dimensional version of these matrix product states known as PEPS, which has just the same ideas. We have these virtual EPR pairs sitting around here, then we apply local projections. We get now a 2-dimensional state, a state of a 2-dimensional system. A sort of more interesting and intriguing structure is this structure called MERA over here. So this is a 2-dimensional network, but it describes a 1-dimensional space. So the only open indices are supposed to be at the bottom. Everything else is being contracted. And so that's a sort of self-similarity to the circuit, to this network that sort of has interesting physical meaning. And so this, for example, it is sort of well established that these left-hand side ansatzes, they work well within a quantum phase, within a gapped quantum phase, whereas the right-hand side ansatz is sort of well suited to critical systems, okay, roughly speaking. And so this has been very sort of exciting and useful from a numerical perspective. Each choice of such network structure, which is usually sort of guided by intuition and experience, gives rise to a variational class that we can use for numerical methods. And if we don't need too much virtual entanglement sitting here on these virtual bonds, then this is an efficient variational class. Another interesting aspect that is not for classical but for quantum computers would be that some of these networks we can also interpret as quantum circuits, for example, the right-hand side one. And so actually that is not only a prescription for doing a classical calculation, but also a quantum calculation on future quantum computers. But the main takeaway message is that whatever geometry you choose, this will carve out some little subspace, some little corner in Hilbert space, and the hope is, or the goal is to design these families such that they actually target the physics that we care about. Now, sort of from a more theoretical perspective, how do we go about choosing all these different network geometries? So what is the guiding principle? And one sort of very fundamental principle is a the following. It's a very basic fact about any tensor network state, whatever the network looks like, and is a bound on the kind of entanglement that is sort of supported by any state represented by such a tensor network state. So what does this bound look like? Well, suppose we have again this mirror tensor network. So remember that our physical qubits are sitting at the bottom. Everything else is being contracted. Everything else is virtual. It's not a physical subsystem. And suppose we focus on say an interval subsystem like the qubits in this blue interval over here. Let me call those the A qubits. Now, the fundamental bound on the entanglement entropy in any such network is the following, namely that the entanglement entropy of in any quantum state, the entanglement entropy of subsystem A can be upper bound in the following way. Let's find a cut. Let's find a minimal cut through the network that separates these A subsystems from the other subsystems, sort of the A complement subsystem sitting over here. That would be this red cut. Let's just count how many bonds we cut in this network so how many bonds do we cut along this minimal cut? And let's multiply it by the number of EPR pairs that correspond to a single such bond. So previously in my example, there was only one EPR pair per bond, but I could have many in general. So let's say we have n EPR pairs per bond, and then we have gamma of A, many bonds that we have to cut in this way, and then we get an upper bound, a geometric upper bound on the amount of entanglement supported by this network. In particular, if we didn't need to cut any bonds, then we would have zero entanglement entropy, which would tell us that the A subsystem is completely uncorrelated from the rest. Okay, and so in this sense, tensor networks geometrize the entanglement structure of a quantum state. It sort of enforces a particular entanglement structure, and thereby an organization of quantum information in these states. And sort of this fundamental link between entanglement and geometry is sort of what we want to push a bit further and sort of try to connect even to space or space-time. But before that, I should say that also from a theoretical point of view, based on such ideas, tensor networks have been a very useful, insightful formalism. It has allowed us to get a grasp on quantum phases, classifying topological order, but also on ideas such as the renormalization group, and something that we'll talk about in a bit. Sort of any tensor network we can think of giving sort of some sort of a duality between this description of the physical state over here and then what's going on all of these bonds. And so this is sort of a form of a bulk boundary duality that is not unlike ideas such as the holographic principle that we'll talk about in a bit. All right. So let's change gears slightly. So in tensor networks, you had this geometric upper bound on the entanglement. So there was a connection between entropy and well, here it would be like a length, but we can think of this more generally as the area of some surface. So here's another situation where we have some kind of entropy and a relation to area, and then this is of course the context of black holes. So it has been sort of early on discovered that black holes are supposed to have an entropy, and that this entropy, which is sort of due to, well, this observation is due to Bekenstein and Hawking, and so it's called the BH entropy, therefore Bekenstein-Hawking of black hole entropy. It should actually be not only bounded but proportional to the area of the event horizon of that black hole. Okay, and so there's a proportionality constant, 4 times the Newton constant. And that is a bound that is supposed to hold sort of due to even just thermodynamic considerations, okay? And that is very surprising. It is surprising because if you have some spin system, then maybe the ground state will satisfy an area law. But then if you sort of excite things more and more, we will expect that we find some volume law. But some of this is saying that some of the objects in nature that sort of richest in entropy or densest in entropy, black holes actually satisfy an area law. And so a theory of quantum gravity, whatever it looked like, should really give a microscopic explanation to this observation. And well, I guess it's really hard to see here. So what was, I guess there was a similar picture two talks ago. So this is sort of a tessellation of sort of I guess an artistic rendering of sort of a tessellation of a sphere, and there were sitting little bits on it. So one such microscopic explanation could in fact be that the degrees of freedom of our theory of quantum gravity should be associated not with volume, as it usually happens to be the case in local quantum field theories, but actually with the surface area of the system. Okay, and so this has sort of led further to sort of a more general proposal known as the holographic principle, that maybe in fact all information in a region of space or space-time should be equivalent to and maybe more conceptually more appropriately being representable as a hologram living on the boundary of that region. So this is the holographic principle to Susskind and 't Hooft. Now, of course, it's not clear how you should realize such a thing, and there is I guess there are certain ideas, but maybe one of the most systematic way of realizing this idea of a holographic principle is known as the ADCFT correspondence or gauge gravity duality discovered by Juan Maldacena. And basically, I mean, we'll be extremely superficial here, but basically this is the idea is that there's supposed to be some, so we are in a, say, d plus one dimensional space-time, so say time goes up, and say space would be two-dimensional here. We call the interior of the cylinder the bulk, so really this geometry should be anti-de Sitter space and say 2 plus 1 dimensions. Now, in this bulk, there lives a certain theory. We want to think of it as a theory of quantum gravity. Usually there's some strings around and so on and so forth. But the point is that in this duality that Maldacena discovered is that the same theory could be described by a non-gravitational theory, an ordinary local quantum field theory, in fact, a nice conformal field theory, living purely on the boundary of the cylinder. Okay, so on the boundary, what does it look like? Well, it has one time direction and one spatial direction would be sort of, you know, this sort of circular coordinate over here. So I'm glossing over many details, but that's sort of the cartoon picture of what's going on. Now let's focus on a time slice. So this would be a time slice. We just chop the cylinder at a certain fixed time. So so we would have a one-dimensional boundary theory and a two-dimensional bulk theory, and the new coordinate is this radial coordinate, and sort of this, you know, the sort of an artistic rendering due to Escher of the hyperbolic metric that's living on this time slice in the bulk. Okay. Now, this is supposed to be a duality between two physical theories. So what this means is that there should be a dictionary relating quantities in the bulk to quantities on the boundary. And this is a dictionary that has been partly understood in certain limits. There have been many checks in those cases. But one particular sort of ingredient, one particular entry in this dictionary is one that is of particular interest to us today, and it is a connection between entropy and geometry. And it's sort of very reminiscent of this black hole area law that I showed you before. And so what it says is the following. Suppose we look at this boundary, so the boundary is an ordinary state of some conformal field theory. Maybe I want to ask, what is the entropy of some boundary subsystem, such as the subsystem A? Then there has been a remarkable proposal some decade ago by Ryo and Takayanagi, and they proposed that, in fact, in an arbitrary such setup, as long as there's some semi-classical notion of a bulk geometry, the entanglement entropy of this boundary subsystem should not only be bounded, but in fact be equal to or proportional to the minimal area of any surface. So here would be a one-dimensional surface, the minimal length of any such surface that is, you know, has the same shape that is homologous to A, but which goes to the bulk. So there's this minimization problem, and it looks exactly, you know, like what we saw in tensor networks. It's sort of very reminiscent of the black hole case if you had some horizon sitting in the middle and so on. And so that is sort of the key connection that I want to focus on. And early on, of course, it led to people to ask, you know, what is the microscopic mechanism? Why should something like this be true? Is it extremely fine-tuned about ADCFT? Is it something generic? But it also gives rise to this very concrete question, and this was first observed by Brian Swingle. You know, maybe that's actually a conceptual description of what's going on in these boundary states in terms of a tensor network that's sitting in the bulk. Because as we just learned some slides ago, any tensor network satisfies an inequality that looks exactly like this, where 1 over 4g is replaced by the sort of the number of microscopic degrees of freedom, the number of Bell pairs per bond. And so maybe, you know, maybe that's actually quite generic phenomenon. Maybe you can cook up toy models based on tensor network ideas that sort of implement some sort of bulk boundary duality. And so that is really what I want to focus on in the remainder of my talk. Okay. But I mean, it is quite a tantalizing prescription, right? It sort of relates an information theoretic concept, an entropy, or an entanglement between the subsystem A and its complementary subsystem directly to geometric quantity, right? So that you have no entanglement if space is disconnected. That is a particular dramatic case. And sort of, you know, there's this idea that maybe these two things, entanglement and sort of connectivity of space-time, may actually be the same thing in sort of disguise, okay? And we want to try to model such things in very simplistic toy models, okay? So how would you go about finding such a toy model? Well, so as I was saying, we want to find exactly solvable toy models of such holographic duality, so of this holographic principle, sort of in a general sense. And basically, there's sort of the easiest thing that you could do is you just put a tensor network on this time slice. You, by this tensor network, define a state living on the boundaries. That's what's illustrated here, sort of the zoomed-in version of what I said before. And well, the question is now, of course, how do you choose the tensors? Okay, and in a sort of a toy model, we really want to choose those tensors in a very simple way. And so basically there's two approaches. One is due to Haro, Preskill, Pistovsky, and Yoshida, which is sort of to choose these tensors to be in a fine-tuned but very simple way, so known as perfect tensors. Another approach that I was involved with Patrick Hayden and collaborators is to just simply choose those tensors at random. So that's sort of a disorder model, like we know it from other kinds of physical systems. And it turns out that this is actually enough, so that's a good choice. And what we find is that for large n, that is for if each of these bonds correspond to many qubits, and the only thing we do is we choose these tensors at random, we find exactly that this Ryuta-Yanagi law emerges. So somehow, in such a situation, the only thing that we prescribe is the geometry. Everything else is sort of chosen at random, sort of without introducing any new symmetries. It turns out that this Ryuta-Yanagi law is plainly emergent in such a situation. Okay. And so that's sort of a nice check, right? Maybe you might ask, okay, why should this be true? So I guess in principle, I could give you 3 explanations. Let me maybe just in the interest of time focus on one. And it is sort of the perfect tensor interpretation. So what is going on here? So what's going on here is that a random tensor, so remember we choose these little guys sitting everywhere here at random. These little tensors actually are very close to unitary transformations from any subset of the legs to any complementary subset of the legs, as long as the dimension of what goes in is less or equal to the dimension of what comes out. And so it turns out that suppose we now focus on the subsystem A and the corresponding minimal cut that goes across here, then there's all these Bell pairs, all these EPR pairs that go across, and then we have a sort of a wedge, a region over here, and a region over there, and just by gluing together all these little unitaries and orienting them in the right way, we can think of what's going on here is that there's a map from sort of these red these halves of the red Bell pairs over here to the boundary system A, and from the other halves to the boundary system A complement. So as a cartoon, so really this complicated tensor network picture on the left is really equivalent to a picture like so, where we have n times an amount of bonds we cut, and the amount of Bell pairs we cut many EPR pairs over here. We apply some local unitary transformation on the left and on the right, and hence, of course, the entanglement entropy is given exactly by the number of Bell pairs that we introduce up here, because somehow these local unitaries or isometries do not change the entanglement. Now, there's some other interesting interpretations of what's going on here. There's an interpretation that is really sort of really information theoretically in terms of entanglement distillation. There's another one that's sort of more condensed matter-y, so we can interpret this disorder average as some kind of giving rise to an effective spin model and effective ferromagnetic Ising model, and then sort of the emergence of this minimal surface is really a domain wall in the language of Ising physics. But of course, all this also raises the question: is there? I mean, this is sort of a beautiful little like toy, right? But is there any deeper meaning behind this observation that random tensors really have this phenomena? Is there some sort of typicality going on in the microscopic degrees of freedom in the bulk that sort of would allow us to make this picture more sort of realistic or connected, sort of on a more technical level? Another sort of critique that you may have is the following. So this ADCFT corresponds, this holographic principle is really, I mean, this is a full-fledged duality between two physical theories. So full-fledged, a whole dictionary that relates, that does not only create a single tensor network state with funky properties, but it's a whole dictionary that, tells us how to relate many states, how to map observables, and so on. And so how could we go about doing such a thing with a tensor network? Well, what we can do is we can just add new indices to the network. And so what we may want to do is we take the previous picture, but now we add little qubits, sitting everywhere here at the bulk. And so we just add inputs, new inputs, these red inputs to these tensors. And so now this tensor network describes, if you wish, a quantum state that has degrees of freedom both in the bulk and in the boundary, where the red legs correspond to bulk degrees of freedom and the black legs to boundary degrees of freedom. But you can also think of this as a mapping from bulk degrees of freedom to boundary degrees of freedom. Okay, and if you choose the parameters right, this will be a unitary mapping, and it's really or an isometric mapping. So it's really encoding these bulk degrees of freedom into the boundary. And in other words, the logical bulk states here are being encoded into the bulk states we can think of sort of the logical qubits, like in a code, like in an encoding. And the boundary qubits are the physical qubits that are sort of, subject to errors and so on. And you should think of this as a toy model of how in this holographic duality, in this ADCFT corresponds, bulk quantum fields get encoded in the boundary theory. Okay. Now, maybe that's the last thing I want to focus on. Actually, let me just check the time, if I should indeed focus on this. Right. So maybe, yeah, maybe very briefly, you could ask, now you have this mapping, there's a geometry in the bulk, there's a geometry in the boundary. You may ask, how about the locality of this mapping, right? So in particular, you may ask the following question. Suppose you have a qubit sitting here in the bulk. Can we reconstruct this giving knowledge only of part of the boundary, say the subsystem A, okay? And it turns out that the answer is yes, you can do so if and only if this qubit that you care about, this logical, this quantum information here, is sort of enclosed by the minimal cut between A and A complement, something that's called the entanglement wedge in sort of this business. And it's an interesting observation that this region is not unique, right? So here's one choice of A, here's another choice of A. And so that has led to a puzzle in the community. So why should there be two ways? Does this violate some no cloning thing, and so on and so forth? But in fact, it was sort of recognized that this redundancy is actually a feature and is exactly the feature of a quantum error correcting code. Okay, so that's an interesting observation. So somehow, what it means is that the quantum information that's sort of sitting further deep down in the bulk is actually better protected against errors. What are the errors? The errors are erasures of the boundary. Okay, so we are basically, the idea is that if I give you access to boundary system A, it's the same as saying we lost all the quantum information, the complement. So this is a quantum erasure code. Okay. And it's sort of connected to ideas from RG and so on and so forth. Maybe the last thing I should say is, yeah, maybe let me just say that indeed this behavior, this error correction property in what is called the entanglement wedge is something that we know from the ADCH correspondence that was predicted there. So it's nice that these toy models reproduce this. Another thing that they reproduce, another thing you could ask about is suppose we put in some entangled state, right, into this code in the bulk. We will get some boundary state. What are entropies of this boundary state? And we would expect that sort of in leading order, we just get this Ryutake-Nagy law, this area law term, and that is indeed what happens. But there's a sub-leading term, there's sort of a next to leading order term, and that term is actually the entropy of the state restricted to exactly this area, again, this area enclosed by the minimal surface, okay? And what this means is that really entanglement is now completely equivalent to geometry, and in particular the geometry in the bulk is being encoded into entanglement in the boundary. And the idea is the following. Suppose we want to change the geometry in the bulk, so we may want to add an additional leg in our tensor, an additional connection in our tensor network. Now we know that this is of course exactly the same as introducing local entanglement into this code. So this is this red picture. But now the entanglement in the code will be equivalent to entanglement between A and A complement on the boundary. And so this implements sort of an idea to Maldacena and Susskind known as the ER equals EPR proposal, which is sort of saying that connectivity in the most drastic case, Einstein-Rosen bridges, wormholes in the bulk, equivalent are dual to entanglement in the most drastic case, EPR pairs in the boundary theory. Okay. So there's other games that one can play, but maybe let me wrap up. So the idea so the message that I want to bring across is that the holographic principle predicts that there should be some connection between sort of the connectivity of space and space-time and entanglement. Okay. And what quantum information theory I think can offer is sort of both these toy models, of which I sort of gave you a glance, but also sort of interesting mechanisms rooted in entanglement, this concept of tensor networks and the principle of error correction. And by this, give sort of new insight into these connections. And I guess you notice there's ongoing work, and so there's many open and interesting questions. But maybe I should close for today. Thanks very much.
Okay, thank you very much. So maybe we have one question for a short time. And maybe I can ask the next speaker to come and set up while we're waiting.
Hello? Yeah. Thank you very much for your talk. I imagine it was very difficult for me to completely follow everything. Of course, it's a very complicated thing. But could you at least enlighten me with where entanglement is important for this thing? In the sense that if I would change in your talk, and sorry for the weird question, but entanglement with some sort of link, wherever other thing, where is really necessary entanglement? Because it's all about entanglement and space and time, but I don't see where entanglement really plays a role.
Right. So what's happening here is that sort of we set up these tensor networks in geometric way. So in principle, there's just links. There's some graph or some geometry, but then we use this geometry to define a quantum state. right? And this is this tensor network construction. We actually put tensors at all the vertices. The links become bell pairs. And so we have a mapping from something geometric, basically this graph structure, to something to a quantum state, a many-body quantum state, which is this boundary state. And the idea is that the geometric properties of the geometries that we started with have an equivalent representation in the properties of this quantum state. So in particular, things like connectivity will get mapped to things like entanglement on this boundary state. And that is, and so that's the core idea. And part of the reason why we want to do is because we want to sort of implement realizations of this idea of a holographic duality, of a duality such in the ADCFT correspondence, but in a very simple sort of conceptual framework, and not in sort of these very complicated, larger and strongly coupled conformal field theory setups. So that is maybe a short answer.
Okay. Yeah, it's just that it seems like an assumption from the beginning already. Then you already put that this link is this entangled pair, but there's no reason why it should be. At least
well, I mean, I sort of, it's like if I define an Ising model to you, I add some, ferromagnetic interactions or something, and you told me I put them in there. But indeed, right? Yeah.
The same talk saying is Ising coupling.
Say again?
You could do the same, saying that this link is Ising coupling.
Well, you could try to do such a thing, but you would not be able to reproduce all these features, right? So you would miss certain aspects. For example, I mean that could be, say, a classical model that you get, right? So that, for example, in that case, there would be no sense of doing, say, modifying the quantum state in the bulk and getting a response on the boundary. So that is something that we would like to have in a duality of two theories, but it would not be something that would be obvious how to do in, say, a classical Ising model or something. Okay. Yeah. Thank you.